This is going to be case study 3 by me, Hunter Castle. So just a quick overview of what I'm going to go over. I'm going to go over a problem. Then I'm going to go over 3 separate cases. The first one's going to be finding the steady state error for no implementations on it. The second one's going to be steady state error improvement. And then the third one's going to be steady state elimination while adding some separate compensators. So first, it's going to be the design vehicle. This is just going to be a little sub that is going to be able to pitch up, pitch down, go up and down in the water. And then the case A is going to be finding the steady state error. For this UFSS vehicle, we're going to find the steady state error of the system, assuming K2 equals 0. Then we're going to find the desired overshoot from the value around the table, a value found on the table using the column for the birth month and the row for my birthday. So using this, my birthday is August 8th. So I'm going to go with 8 to 8. And I'm using a damping ratio of 0.397. So the system, this is going to be the system. This is going to be the vehicle dynamics. This is the actuator. And this is the pitch gain. This is going to be helping to correct it. And then this K2 right here is basically going to be 0. So we're going to have a 0 feedback loop right here that we're going to cover in our MATLAB simulation. We're going to have to combine all these blocks. So this one's going to be in series with this. So we're just going to multiply this by this convolute in MATLAB terms. I'm going to take the feedback of 0 of this whole system right here. And then I'm going to multiply by this negative K1 gain. And there's also this extra feedback loop down here. So we can have the open loop transfer function so we can find our root locus. And then for the closed loop transfer function, we're going to take the feedback of 1 of this whole system to get the closed loop transfer function. So once we got that open loop transfer function, we plotted it with a gain of 1. And then we found our gain at our damping ratio that we had, which is 0.397. I couldn't get exactly, so I'm just going to assume 4.1 for this, for my K. And this is going to be the final open loop transfer function that I talked about earlier. And we're going to basically just multiply these top values by 4.1. We're going to get this closed loop, open loop transfer function final with the correct K. Sorry. And then from that, we're going to determine the steady state error. So we saw that it was type 0, so we're going to take the limit as approaches 0. We're basically going to cancel out all these S's, all these S's. So we're just going to have this right here, 0.4459, divided by this right here. And then once we solve that, we got 10.7265. So we got a steady state error of 1 divided by 1 plus Kp, so we plug in this value to right here, so it's 1 divided by 1 plus 10.7265, and we got this as our steady state error. So in case B is going to be the improvement. We're going to go over improving the steady state error by a factor of 10, designing the compensator, the analysis of the transient responses, the MATLAB simulation comparison, potential improvements, and we're going to go over all of these in these next couple slides. So first, I chose the system compensator. I wanted to use a lag compensator. This is going to be a passive compensator. We're going to define a 0 and a pole location to improve the steady state error. So to improve it by a factor of 10, we're going to have to go through these steps. We start with our Kp from the last original solution. We're going to just assume a pole at 0.001. We need the P to be less than Z. So as you can see right here, from 0.001 to 0.108, this is true. This case is true. So to solve for it, we got to get the steady state error we originally had. We're going to divide it by 10 because we want it to be 10 times greater. Then we're going to plug in this new steady state error to the Kp equation. We're going to have 1 minus the new steady state error divided by the new steady state error. We're going to get the improved Kp, which is going to be the Kp new divided by Kp. Then we're going to multiply this by the original pole that we chose right here, and we're going to get the 0 value. These are the numbers that we got out from this. So it's basically just going to be 10.831 times 0.001. We're going to get 0.0108 for our 0. So now we can implement the system. We're going to basically put that GC and just multiply by that top value that we had for our open loop transfer function earlier. We're going to find our new K with a K value of 1 originally. We're going to solve it here. I got 0.395, and then 3.91 is going to be our gain. We're going to rework this and then plug that K value back in to our open loop transfer function to get a final one, along with a GC in it. And then we're going to, this is just a comparison of the root locuses that we had. So you can tell they're fairly similar, but the red little dots right here, the new pull and 0 that we have right here, it's not a drastic difference in the system, but we'll see a little bit more later about how much different it actually is. So this is the step response comparison. This is a zoomed in value right here. This is the non-zoomed in. So you can see we approximately improved by a value of 0.1 as this is our uncompensated, and it dies off right here. This one the compensated takes a lot longer to die off, but it's all things that are worth it. I mean, we're going to be improving our stage there by a lot, and it might just take a little bit longer, but there's other things we can implement to improve it. And you can see it rises a little bit higher, and then it just keeps going up. So even with our original final spot right here, it's already a lot better than our other system was, or ever gets to, which is good, but we can see that through our system characteristics. I used MATLAB, and I used this function right here to basically just print out all the values. So the rise time takes a little bit longer for our compensated. Settling max takes a little bit longer, but as you can see, the settling at max that we got right here is a little bit higher, which we like, and we want that to be higher. Our peak time takes a little bit longer, but like I said earlier, it's worth it because we're going to be improving our steady state error by a very large amount. And then there's other compensators that we can add into it to make it better. And like I was talking about, we can add a PD or lead compensator to improve our system's transient response to closer to the uncompensated response for the desired transient response. And then in case C, the steady state error elimination, we're going to be designing a controller or compensator to eliminate steady state error. We're going to be designing this with our new GC of S. I'm going to show the MATLAB simulation. I'm going to be doing the comparison of the different cases, go over the advantages and disadvantages of passive compensation in both cases, passive versus active compensation. I'm going to go over a couple of improvements we can make. So first, I chose the system compensator. I'm going to be doing an active PI compensator. We're going to just choose a 0 close to the origin for this. And as you can see, we don't have the pole value in this one. So this is going to be going over the same steps we took through the original time. We're going to be finding K from the GC, our new GC times our original open loop transfer function. We're going to have to convolute the numerator and the denominator. And then we're going to be plotting on the root locus with 1. And then we're going to get our gain of 3.92, which is a new gain. Our value of 3.96. I couldn't get exactly 0.397, but you get the idea. So the new steady state error is going to be type 1, so the new steady state error will be 0 because our KP, as our limit of S approaches 0, is going to be equal to infinity. And then, as you can see, 1 divided by infinity is basically 0. Just a really big number. 1 divided by a really big number is basically just going to be 0. So the root locus comparison, we're going to be going over this one again for our new system. And as you can see, it's just going to be basically relatively the same thing. A little bit of improvements if you zoom in, but nothing too drastic. It's just going to be shifting a little bit to this way. So our new step response comparison. This is our new compensated system. And as you can see right here on the zoomed out, it improves by a factor of about 0.1 in this case. And as you can see, it stops right here before it has to loop back, and then it takes a really long time right here. And about the same time in manner, it's improving by a little bit, which is always a good case. And right here, you can see it just rises a little bit higher. When it goes down, it doesn't fall as far, and then when it comes back up, it rises back up a little bit higher than the other one, and we want that. So the same thing with the system characteristics of this one. And as you can see, it kind of followed the same path, but this one just took a little bit longer, if I remember correctly. Sorry. than the other one did, but other than that, for the most part, all the numbers kind of did the exact same thing. I'll compare them in a little bit more detail, a little bit closer later. So the comparison of our different cases between case B and case C, the lag compensator is going to be the passive compensator, and then the PI controller is going to be the active compensator. And then a little bit more information on both of these two things. The lag compensator typically involves adding a pole and a zero to the system's transfer function, where the zero is placed closer to the origin than the pole. This setup is going to be increasing the system's phase margin, instability, potentially at the cost of a slower response. Compared to the active compensator, where the PI controller integrates both proportional and integral actions into a control system, it adds a zero to the open loop transfer function, improving the system's responsiveness, reducing the steady state error without affecting the type of the system. In summary, the choice between a PI controller and a lag compensator depends heavily on the specific needs of the application. PI controllers offer dynamic error correction and adaptability, the cost of complexity and power, while lag compensators provide a robust, cost-effective solution at the expense of responsiveness and flexibility in the transient performance characteristics. So basically, this is just listing over both of the different pros and cons of them. And you can really use either or. You can honestly also use a combination of both of them, which is going to be the probably most effective way in most every situation, is just a combination of both, so that you can get the best of both characteristics while implementing these new compensators. So when you compare both of these top two are going to be case B, and then the bottom one's going to be case C. You compare both of these, you can see that in the original step response for case B, it's going to be taking a little bit less time to get to its final value. So if we wanted some of the characteristics of case C that we went over, while adding just a PI, we could help improve that by using that one, where you have a shorter settling time of about 100 seconds compared to the other one, where it takes much longer, about 100 more seconds. You can also see that this one has a little bit steadier of a decay until it reaches it, compared to the other one. It's kind of like a jump. It kind of comes up and boom, goes up a lot quicker than the other one. So how to bring the lead compensated system's transient response closer to the uncompensated response of the desired transient response? We can just add a PD or a lead compensator to do this. These are just another two compensators that are out of this very large amount that we could use. I only went over a PI and a lag compensator. In these cases, we can use a combination of the PID, lag, lead. And then this is just kind of the list of what they do. So overall, these really help improve systems, and if you use them correctly, you can really greatly increase the system's overall functionality and what it does in general. That's it. Thank you.